The parametric equation represents a mathematical expression of a set of functions where variables are typically determined by a parameter, such as time. In 2 dimensions, a parametric equation often takes the following form. T is the parameter, and x and y are functions that vary with the parameter t. Using such equations allows the representation of the changes in x and y over time t. Let's consider the following case. X equals t plus 1, y equals t squared. Let's find the values of x and y for the interval of t in -3 and 3, setting integer values for t. Find x values. Find y values. Plot the graph. We observe that as t increases, the graph shifts to the right. This is known as the orientation of the graph. Now, what if we extend the interval of t to all real numbers? We expect to see a parabolic shape formed by connecting all 7 pairs of points we found. To express the parabola in rectangular coordinates, we eliminate the parameter. Since x equals t plus 1, t equals x minus 1, and since y is the square of t, substituting t yields the equation of the parabola. In the case of the unit circle, which we learned in the previous precalculus class, it can also be represented as a parametric equation. Let's explore the following example. X equals 3 cosine t, and y equals 3 sine t. This represents a circle defined by the parameter t. In this case, as the values of t vary, creating different values for x and y, it traces the trajectory of a circle. Transforming the given equations into expressions involving cosine t and sine t, and substituting into the Pythagorean identity, we obtain the equation of the circle. This is a circle centered at the origin with a radius of 3. Let's visualize it graphically. First, creating a table, we find that at t equals 0, x equals 3 and y equals 0. At t equals pi over 2, x equals 0 and y equals 3. At t equals pi, x equals -3 and y equals 0. At t equals 3 pi over 2, x equals 0 and y equals -3. At t equals 2 pi, we return to the initial position with x equals 3 and y equals 0. Connecting these points creates a circle. As t increases, we observe that the points move along the circle in a counterclockwise direction. Let's solve the following example problem, commonly known as projectile motion. When visualizing the projectile's trajectory, we can observe that the velocity of the projectile is divided into horizontal and vertical components. To calculate the horizontal distance traveled by the projectile, we use the formula, distance equals speed times time. For the vertical distance, we employ the position function. Substitute the given conditions into the equations. Given that the distance to the baseball field's fence is 400 feet, we substitute 400 into the equation and calculate the time it takes for the baseball to reach that distance. The time is approximately 5.41 seconds. As the parametric equation allows simultaneous representation of the changes in x and y with respect to time t, substituting t equals 5.41 seconds into the y equation reveals that the vertical distance is about 12.3 feet. If you set the graphing mode to parametric on the calculator and plot the graph, you can confirm this. Therefore, the baseball will not clear the 15-foot-high baseball field fence. See you next time.